All right, I think we're going to go ahead and get started. Welcome to another session of Nano at Tech. Before I introduce today's speaker, just a word about our next speaker on March 12th, and that will be Professor Sungjun Jang from the School of Material Science and Engineering. So it's a pleasure to have Professor Farrokh Ayazi with us today. I was just saying we last had him speak in this seminar series in 2015. Most of you probably were not here at Georgia Tech in 2015, so this is all be new to you, and I assume it's new material anyway. Farrokh got his bachelor's degree in electrical engineering from the University of Tehran before getting his master's and PhD also in electrical engineering at the national champion University of Michigan, go Blue. And then came to Georgia Tech in 1999, where, as you can see on the slide, he is the Ken Byers Professor in Microsystems and Electrical and Computer Engineering, and as well as Regents Entrepreneur. He is a co-founder of a couple of companies, including Qualtray, which was acquired by Panasonic, and the current one, Stethex Microsystems, which was formed in 2019. He is a fellow of IEEE, the National Academy of Inventors, Career Award winner, among many other honors and awards. And with that, I will turn it over to Farrokh.
Can you guys hear me fine? Yep, okay. Thanks so much, David, for the introduction and also for the invitation to speak at this seminar series. It's a pleasure to be here. So I'll be talking today a little bit about the research activities in my group, in my lab, Integrated MEMS Laboratory, as well as providing some historical perspective in terms of what has been done in the field of MEMS and microsystems over the past 20-some years ago, and hopefully talk a little bit about where is the field heading to, and what are some of the future areas of research and development. So my group does a lot of work on MEMS resonators. And for those of you who are not necessarily familiar with MEMS resonators, basically the device is a micromechanical structure, as is shown in a cartoon here, that is suspended via some mechanical springs. And you can start imagining that, the mechanical springs are not necessarily a must, as long as you can levitate the device or have it somehow supported through other means. And then you have these yellow plates that are symbolizing transducers. So transducers are in charge of converting mechanical energy into electrical energy or some other form of energies. So the governing principles of operation of this device is nothing besides the Newtonian mechanics, and is a second order differential equation for the displacement x of this proof mass, this suspended mass, and F is the force that is being applied to this device through the action of these transducers or through an external means. And if you now start plotting the response of this micromechanical device in terms of what the displacement is, amplitude response as a function of the frequency of excitation, what you see here is that there is typically a resonant frequency for this structure, and the resonant frequency is where the ratio of omega over omega n is equal to 1. And you see that in some instances, the response starts peaking. And that the level of this peaking, you see that I've highlighted it by Q. Q is quality factor and is a measure of dissipation in this micromechanical device. So if the device has very small dissipation, you're going to have a very large Q, and the Q can actually get into tens of thousands, even tens of millions. And as such, for a very small force, you can have a substantial displacement. And that can be used as a very sensitive measurement mechanism or sensing mechanism. And then, of course, you can control this damping factor zeta, and as you can see, Q is inversely proportional to zeta, it's 1 over zeta. And the Q factor has limitations from a number of different mechanisms. It can be limited by the air damping that is surrounding the resonator and the air that is trapped between the transducer and the device itself. It can be due to interaction of the thermal fields and elastic fields inside the structure. It can be due to clamping losses. So the clamping losses is basically what is attaching to the resonator and clamping it to the substrate. So think of it as a funnel that would basically sink acoustic energy into the substrate, and whatever is lost usually doesn't come back in a constructive way into the resonator. So we just assume that it is a lost energy. And then finally, you can have losses due to the surface mechanisms. So these surfaces, as long as they are etched through these chemical processes that we use in the clean room, they're not going to be perfect. They're going to have dangling bonds or defects that would cause additional dissipation in the resonator. And finally, losses due to the material itself. And these relate to the phonon-phonon interactions inside the material that would eventually limit a suspended resonator to the losses that are intrinsic to the material. So the big difference between the MEMS resonator and, let's say, another resonator that is built using electrical component. Let's say an inductor and a capacitor, you can put them in series or in parallel with each other and you can create a tank circuit, right? That's how we make oscillators as electrical engineers. So those inductors and capacitors, when you talk about their Q factors, they are typically in the order of 10 to 100. A lot of times it's even less than 10 if you use CMOS devices. You may find tricks to improve it to 100 or maybe 1,000, but you can never really get to Qs that are in the million or even in some cases much higher than a million range using electrical components unless you use some sort of a cooling mechanism or some quantum mechanical effects or quantum effects in general. So this is really the big advantage of using MEMS resonators, which is tapping into various small dissipations of the acoustic fields inside mechanical structures to get much higher Q factors. So when did this whole MEMS business start? I like this slide because that is in particular for some of you guys who might be younger, you may not know that MEMS started out as actually as a resonator. It was the first known MEMS device was developed at Westinghouse back in 1965. The person, Nathanson, who actually developed this device, the resonant gate transistor, used a transistor but with a suspended gate that was free to move, okay? So there was no oxide separating the gate of this transistor from the channel area. And the interesting thing about the operation of this device is that when the incoming signal to the gate of this transistor coincides in frequency with the resonance frequency of this cantilever beam, it will cause a very large current to flow between the drain and source of the transistor. It's basically amplifying the G sub m of the transistor to get a gain at the resonance frequency. So as a result, you will get a response that is only passing the signal through when the signal is coinciding with the resonance frequency. Now imagine instead of one beam, if you have two beams, two cantilevers acting as the gates, and they are coupled at the very base, as you see here, then these two will actually create a passband response, a pretty wideband passband response, and this is what is known as a frequency-tuned amplifier or a bandpass filter that is integrated with some level of gain in the electronic side as well. So this device was way ahead of its time when it came out. The idea still is being pursued by a lot of researchers in the field to actually make front-end filters for our cell phones. And even to this day, people are not able to integrate high-quality resonators with electronics on the same chip to integrate all of them on a single chip and create a bandpass filter with electronics integrated. So this was back in 1965. The device that was used to build this cantilever gate was gold, electroplated gold, right? So it had a lot of drift. It wasn't high Q enough. Now, let's take a look at the journey of MEMS from inception up until about 2000. A lot of work went into developing MEMS devices, mostly using thin film structures like polysilicon, surface micromachining, or metal films that were deposited. So take a look at this beautiful picture on the left side. This is an example of the Sandia National Laboratory Summit process, okay? Think about complexity and compare it to CMOS. 5-layer polysilicon surface micromachining process, 14 masks, 240 process steps to create these microgears that would actually cause a lot of mechanical mechanisms, including out-of-plane mirrors. So you could push a mirror to come out of plane and create an optical lab on a chip. So that was one example of what was done during this period with a lot of support from the government. Another example that came from industry was Texas Instruments' digital micromirror device. So this is the technology, some of you might have heard of the digital light processing. So these tiny plates were tiny mirrors that were processed on top of a CMOS circuit. And in a chip of about 2 centimeter by 2 centimeter, there were a few millions of these mirrors integrated. And by controlling these movable mirrors through the electrostatic forces that are being applied via these electrodes to the mirror, you could actually project the light with different colors onto a bigger screen, and that was, in fact, how a lot of these overhead projectors were actually projecting on the screen initially. Some of them now have changed to LED-type devices, but these by far were one of the most profitable businesses for Texas Instruments at the time, okay? So when you go back to 2000, this was a very successful business for TI. This one was not so much successful. The reason was that most of the mechanical devices, if you are really trying to get a mechanical action out of it, you have to use a little bit more mass. So these surface micromachine devices didn't have enough mass. So what happened at 2000 was that there was enough advances in the wafer bonding technology and grinding wafers that enabled introduction of the silicon on insulator wafers, okay? So the silicon on insulator wafers were available before that for CMOS processing through a process called SiMOX, which is implanting oxygen into the silicon and creating a very thin layer of silicon to create transistors on top, and then isolated from the rest of the substrate through this oxide layer. But as I said, the thickness of the silicon would be limited through a SiMOX process. The bonded SOI, the nice thing is that you can actually get to any type of thickness of the device layer that you want, anywhere from 5 to hundreds of micron. And you can also tailor the thickness of this buried oxide layer, okay? So you would go and order this online. So there are, even to date, there are companies that you can get your custom-made SOI wafers with any type of silicon handle and device layer, regardless of the doping. You can have all sorts of doping that you want to have, even highly doped 111 silicon versus 100 silicon. You can choose the thickness of the oxide layer. And the beauty of it is that once you get it, then most of you guys probably know about the Bosch process, the silicon deep RIE process that enabled etching trenches into the silicon substrate. You can use that process, literally one mask, to etch these straight trenches into the silicon device layer to create a structure. Then you release that oxide layer through a hydrofluoric acid etching, as acting as a sacrificial layer, and voila, you have now a MEMS device that is ready to use. So with one mask, if you have one of my wire bonders, we have a wire bonder that can directly bond to silicon. So you can even get them to be tested without any metallization. So this process, the bonded SOI, caused really an inflection point in the MEMS development in the year 2000. But it wasn't that alone that caused the deflection point. Another very important factor was the introduction of the multi-physics finite element simulation tools, in particular COMSOL. COMSOL multi-physics came into existence in terms of being widespread use in the universities and also in industry at around 2000. And with that, DARPA also poured a lot of funding into the MEMS development, funding that was pretty much focused on different applications. So these were a couple of very important programs. Initially, it started at around 2000. NMASP, nanomechanical arrays of signal processors. We were part of that. It was really a groundbreaking program in developing MEMS. And the other one was MPG, or micro power generation. So back then, power generation on a chip was also very important. So people look at that application quite extensively. So focus really shifted to now using different materials and devices through this wafer bonding application to enable higher performance devices as well as a large array of applications. So I joined Georgia Tech at around 2000, actually January of 2000. And this was one of our first devices that we made at Georgia Tech clean room in the Petit clean room. This is the work of my former student, Siavash Purkamali, who is a professor at UT Dallas now. So you see that we use that SOI process that we just, recently became available back then at the time. And you see that the thickness is about 18 micron, but the electrodes were made out of polysilicon, filling up these trenches and separated from the body of this disk resonator with a very tiny gap of only 90 nanometer in size. So through the combination of surface and bulk micromachining, we were able to create these structures. And according to COMSOL simulation, this device should have a resonance frequency at around 150 megahertz. And back then, people thought that this is crazy. You're never going to get this thing to resonate. It's so hard. It wasn't back then done electrostatically. People use piezoelectric transducers to get high-frequency elastic fields into the material. But through a lot of sleepless nights, Siavash were able to measure this Q, which was incredibly high, 46,000 at 150 megahertz from this disk resonator by applying a DC voltage to polarize the transducer. And that technology continued. The development, again, this was published in journal form in 2004. And now fast forward about 12 years later, you saw that we actually make a gyroscope out of this technology. The silicon bulk acoustic wave gyroscope, again, is electrostatic gyro that doesn't use any piezoelectric device, but use these higher frequency bulk acoustic wave of the disk resonator. You see the picture of the disk is only 1.5 millimeter in diameter. You see it's pretty thick and is wafer level packaged through wafer bonding again. So wafer bonding played a very important role in development of MEMS. And what you see underneath is the ASIC that is in charge of control and reading out of this device. So this is now, because of these electrodes being patterned around the structure, we had the ability to excite any mode that we were interested in. Some of them are gyroscopics, and some of them are not. So this mode is a gyroscopic mode, which means that it's a degenerate mode that would couple as a result of a rotation around a particular axis to its sister mode. And the performance is typically shown as this Allen deviation plot, which is the noise processes being plotted as a function of integration time, okay? So what does this show you? This shows you that the device measured results is this green curve, and you see that it is actually, as you increase the integration time, the noise in degree per hour goes down until it gets to a plateaued region, okay? The reason behind this plateaued region is the presence of flicker noise in the system. If there was no flicker noise, if there was only thermal noise, as you integrate the thermal noise, the overall noise should go down, should keep going down, okay? But because of the flicker noise in the electronics, you're not getting that. So this device has now a bias instability or best noise performance of about 0.2 degree per hour. And just for you as a frame of reference, the Earth rotates 360 degrees in 24 hours, right? So the Earth rotation rate is about 15 degrees per hour. So this is easily a couple orders of magnitude less than the Earth rotation rate. So you can actually measure the Earth rotation rate with this device, and you can do what is known as gyrocompassing, which is detecting the true north instead of using a magnetometer to do compassing. So there are a lot of cool things you can do with gyroscopes. And the point here was that to tell you that it took a long time still to develop a device that was born out of Georgia Tech research and transfer it to a foundry and get it commercialized. The end use of this device was for autonomous cars, so to enable the navigation of autonomous cars when GPS signal is not available, or if you're deciding to go to an area that the GPS is intermittent, like a parking deck or some, some areas of a crowded city with a lot of high rises like New York City. So this was one example. I want to also show you this other example, which didn't have any separate transducers. It's still a resonator, and you can see how small it is. The scale here is 10 micron compared to a millimeter disc that I showed. So this is a work of, again, Siavash Purkamali, and it is a I-square barred resonator. So it's a bulk acoustic resonator. It's a dog bone shape. We call it I-squared because it has two eyes here. And it's thermally actuated and piezo-resistively sensed, okay? And it doesn't require any external transducer or any additional transducer element. So you simply pass a current from this side to the other side. You have to have a DC current, and then on top of it, you add an AC current that coincides with the resonance frequency of this device. So this AC current would cause cooling and heating of the resonator. And if that frequency coincides with the elastic resonance of the device, you start actuating that resonance mode. And when the resonances occur, now because of a stress at the base, you will actually get a change in the resistance of the silicon. So that's the piezo-resistive effect. So by just running a current, you see these nice resonance peaks out of the device. Qs are in the order of 12,000 and 14,000. Now, a lot of people asked back then, thermal actuation, isn't it going to be slow? Because people have a hard time imagining that things can heat up and cool down in the matter of nanoseconds. And look at the frequency of this device. This was a 60 megahertz device. So you can actually use these for even gigahertz devices without having any type of additional transducers, albeit at the cost of additional power consumption. So this device needed 100 milliamps of a DC current to get a much larger signal out. Of course, if you drop that current, your signal is not going to be as large. Now, moving again into different type of structures, this is what COMSOL multiphysics enabled. That people were familiar with a square Lamé resonator. A square Lamé resonator, if you just look at one of these pixels here, it's how it's going to look like, okay? But people didn't really realize that you can use a higher order Lamé within a frame. So we have now here a rectangular frame. So this thing with a width of W is just the frame. And this is the distributed Lamé mode excited into this structure, okay? Now you can see that these areas are in opposite phase to each other. So to make that happen, you have to have these interdigitated electrodes that are separated from the body of the resonator again with nano gaps. So this was all enabled by this special process that we developed here called the HARPS process. And now look at the results that you can get to frequencies well above 100 megahertz. This is 167 megahertz, and Q is about 77,000, right? So you do need this DC voltage to get as I said, the capacitive transducer polarized. If you take the DC voltage to higher voltages from 3.5 to 17 volts, then the motional resistance drops and you get a much cleaner, larger signal, as is shown here on the right-hand side. So if you have access to high voltages, your performance will get better when it comes to MEMS. And as a result, there are a lot of opportunities on the circuit design side of things to not only get rid of that flicker noise that I showed in the previous slide was limiting the performance of the gyro, but also to take the DC voltages from the 1.5, 2 volts that supply voltages are today up to 17, 20 volts that most of the MEMS need to operate at their optimum point. All right. Now let's switch from capacitive to piezoelectric. It was around 2007 and 8 that very high quality thin film piezoelectric materials became available. And that was basically aluminum nitride. Aluminum nitride, it's a benign piezoelectric material, meaning that none of these are going to hurt the CMOS process in terms of being a nasty doping for CMOS. So it could be integrated with CMOS or processed at the CMOS foundry. And the nice thing about it was people found a way to just use a sputtering and deposit these piezoelectric films on silicon. So now you could use transducers, piezoelectric transducers on top of a silicon material and excite the resonance mode of the structure, and again, having different geometries to enable different functions. So for example, this device had these sensing platforms, like 2 platter at the end. And what would you do is that you would basically functionalize these 2 platters with some sort of a molecular recognition layer. So these will be sensitive to a certain type of molecules available in the environment. Once the molecules get absorbed on these surfaces, it will cause a change in the mass of the resonator, and then it will cause a change in the frequency, okay? So if you build a oscillator out of this resonator, and then expose the resonator to an environment where that molecular recognition layer is being active, then you can actually create a biochemical sensor. So for example, we made a bunch of VOC sensors, volatile organic compound sensors, and we showed that by just cycling the concentration of xylene, which is a type of VOC in the environment, the frequency would shift. Another more sensitive application was sensing ammonia. So this is an ammonia sensor, again, using the same type of device, just patterning the annex platforms with the molecular recognition layer, which was a polymer for ammonia. And you can see that we could actually detect easily 10 ppm change in the ammonia. So this was a device that could detect sub-ppm change in the ammonia concentration. So there are now applications. So why do we like piezoelectric when it comes to gas sensing? The reason is if you use capacitive devices and expose them to air, which is what you need to do gas sensing, the air is going to get in between the electrode, the capacitive electrode, and the body of the resonator. So first of all, it will create a lot of damping because of air squeezer damping. The other thing is that things will get trapped in that gap, and the resonator may not have a long lifetime. So if you have the transducers directly attached to the material, it will have a much more robust and much higher long lifetime. Now, the gigahertz resonators also become available and in a way that was usable for industry because of the aluminum nitride piezoelectric films. So this is an example of a resonator using, again, aluminum nitride as a actuation layer. You see that this device was resonating at 1 gigahertz, and the oscillator that was made by interfacing the resonator with an IC showed very good performance level that was suitable for most of the communication systems being used. Now, people started thinking about, okay, if I couple resonators similar to that resonant gate transistor, I should be able to get filters that are used in the front end of our cell phones. And sure enough, that was also possible. So you see that there are 2 filters built next to each other here, and they are separated very slightly through lithographical changes in the dimensions of the resonator. So basically the same platform, by slightly changing the dimensions of the resonator, you can get 2 filters at 3.4 gigahertz that would be able to serve the front-end filtering in a cell phone application, right? So one particular problem with this configuration was that they're going to be on all the time, right? So you have to basically choose one of them versus the other one, depending on what the incoming signal is. So people had to then integrate switches with these filters to be able to switch one versus the other one. Okay, now let's switch a little bit towards different materials, all right? So we started playing around with a lot of exotic materials. So this is an example of a diamond resonator. So this is a nanocrystalline diamond, and we use a zinc oxide layer as a piezoelectric layer on top. So back then, again, these materials had just become available. We went back to an SOI-like process, but using NCD as the device layer. And sure enough, again, you can get working devices. This is one example of the smallest form factor filters, not at very high frequency, 78 megahertz, because it was a bending mode beam, but it was made out of diamond. Now, after a while, we started looking at, okay, enough with the 2D, let's take a look at 3D resonators, like a wine glass resonator. So the reason we wanted to do the 3D resonator was really to study the dissipation mechanisms in different type of resonators and see how far we can get the Q to be, as high as what number. So these were made out of silicon dioxide. Benoit, who graduated from MEMS a few years ago, and he's still around town here working for Ingenious Micro Devices. He was responsible for making this device. And then it was very hard to have integrated transducers. So what we did to excite resonance and sense it was that we put fiber optical fibers around the perimeter of this shell resonator, and then start shaking it on a piezo stage to excite the resonances. And what we realized that, we could actually see the resonances of the gyroscopic modes. The Q was not as high as we anticipated it to be. It was about 72,000. And this is when we had already measured Qs in the order of 1 million out of silicon resonators. We were expecting the Q in silicon dioxide to be higher just because the thermal expansion in silicon dioxide was much smaller than silicon, and because of that, the thermoelastic damping losses would have been less. So we started looking into surface losses. Remember, surface loss could be a dissipation mechanism. So we did a lot of AFM-type surface measurement, and we saw that actually the roughness was pretty good in these the thermally grown oxide films. They were all in the order of a few angstrom, but maximum roughness can go up to about 10 nanometer or so. But that was a cause of concern. So Benoit then looked at, configurations of the resonator where you didn't have to worry about clamping losses. So this device is actually called a pierced shell resonator. Is clamped all the way at the top at this edge here, but the resonance is concentrated around the trim edge, the inner edge of the resonator, and as such, the support losses are going to be very minimum. And what he saw was that as he changed the dimension of this device, And these are the red dots are what he was measuring. As the frequency changed, the Q did not change. The Q stayed at around 100,000, as is shown here. So that pointed out to the fact that these devices are all surface loss limited in terms of dissipation mechanism, because that is a mechanism that doesn't scale with the dimensions or the frequency of the resonator, okay? And you can see that all other types of losses are going to be creating Q factors that are much larger than what we measured. So this was a way of indirectly measuring the surface losses in silicon dioxide, which is proportional to this delta. Delta is the thickness of the lossy layer on the surface of the shell. So as you can see here, this ratio, which is the thickness of the shell itself over delta, times the modulus of silicon dioxide versus the modulus of that lossy layer, that ratio would determine what the losses, the surface losses in the resonator would be. So longest story short, if you are thinking about getting Qs that are in excess of 1 million or so, you can't really use thin films, because thin films, this ratio of T over delta would be limited. Your thicknesses are small, the delta would be in the order of 1 nanometer or so. So you're going to be surface loss limited and you won't be able to get to extremely high Q factors, okay? Nonetheless, we were set to actually make a micro hemispherical resonator gyro out of a technology that used a hemispherical resonator. And what we wanted to do was to integrate transducers, capacitive transducers around the structure. So this was the work of Peng Xiao, a brilliant student who actually was able to get this thing to work. So this is the cross-section of this embedded shell resonator inside the body of silicon. And what you can see here is that you could actually see as born, without doing any matching or any tuning of the modes, the two frequencies of the gyroscopic modes are slightly separated. So they are supposed to be on top of each other, but because of process variations, they are slightly split from each other. So then we mode match the device using electrostatic forces, and that is shown by the blue curve. So, and later on, University of Michigan actually showed that if you work with these 3D resonators and then you use thicknesses that are much, much thicker than what we use. We use 1 micron thickness. They use 70 micron thickness at the very edges. They were able to actually get to Qs that are at much higher value, about 4.4 million at 5 kilohertz. So this is still to this date, I think, one of the record-breaking Q factors at low frequency devices. But what you see here is that this device is also very thick. It's about 6 to 10 millimeter thick. So planar integration is not going to be an easy job with this type of devices. And in case you wonder how this was made, it was made through a blowtorching process of a fused silica wafer. So the fused silica was melted to actually create this form. Pretty cool process, but it's really not something you can use in high volume. Now, for the last 10 years or so, maybe less than 10, 8 years, we've been looking at silicon carbide as a mechanoacoustic material, okay? And following what happened to SOI, we were really interested in monocrystalline silicon carbide, not polycrystalline silicon carbide. And the reason we were interested in it was, first of all, it has a wide band gap, as you know it. And the wide band gap enables high operating temperature, higher breakdown voltages. You can apply larger voltage across it, and also radiation hardness. So the combination of radiation hardness and high operating temperature makes it a great candidate for space applications and underground exploration of resources, let's say gas and oil. If you want to use sensors in the underground, you would be using a silicon carbide version. In addition to that, it has superior thermal and acoustic properties. You see that the Young's modulus is about almost 3 times higher than silicon. The thermal conductivity is higher. and it can withstand a higher temperature. And now I mentioned this F times Q acquisor, and you see that silicon carbide is about 30 times higher than silicon. That is a measure of the intrinsic dissipation because of phonon-phonon interactions in the material. So silicon carbide has also a very small intrinsic dissipation compared to silicon. But it had been looked at before. So very early on, people used polysilicon carbide to make a variety of devices. So this was backed by years of R&D at Berkeley, Case Western Reserve University. People used thin film membranes to make pressure sensors. And so it was mostly CVD or smart cut processes that enabled 3C silicon carbide formations like this disc, but very, very thin, like what you see here is again 1 micron. And in case you wonder what are these differences, 3C and 4H, these are the different polytypes of silicon carbide. The 3C it has a cubic lattice, while the 4H and 6H have hexagonal lattices. Big difference for the same material. This is why silicon has all cubic lattices. So we were really intrigued finding out that 4H has a different lattice structure than the silicon that we have been working with for a long time. And more so with the fact that, according to literature, the Q factor that you should be able to get out of a monocrystalline silicon carbide should stay much higher than any other micromachinable material that people have been working with, like silicon carbide, so like silicon nitride, aluminum nitride. Silicon is here, this light blue is silicon, and you see it's near quartz. So we were really intrigued to see what is the highest Q factor we can measure. And after years of R&D, we have been able to now create silicon carbide on insulator wafers. So you see that you can actually bond the silicon carbide wafer 40 micron thick. You can actually etch very nice looking trenches into silicon carbide. It is not the Bosch process because it has carbon inside. Silicon carbide has carbon, so it is a self-passivating process. So you just need a high density SF6 plasma etching, but you do need an electroplated mask to be able to etch deep down into the structure. So this has been the basis of a consortium, an industry academic consortium at Georgia Tech. It's called the Silicon Carbide MEMS Consortium. It has about 7 industry members, and it is supported by SEMI-ARL. Initially, it was supported by DARPA before it was transferred to those entities. And you see that silicon carbide is transparent, the wafers, but they come now in 4-inch, 6-inch, and 8-inch wafers. You can micro-machine them relatively easily. Now we have learned how to do it very well. They are still much more expensive than silicon. So one of these 6-inch wafers would be about $1,200 compared to $50 you pay for a silicon. So this silicon carbide on insulator wafer that you see here, after it's all processed, is going to be about 3x more expensive than a silicon on insulator wafer after processing. And then there are certain things that you have to be careful about with silicon carbide. For example, it has a silicon face and a carbon face. So the silicon face has a much lower oxidation compared to the carbon face. So this is a very nice example of a trench etched into the silicon carbide. You see that the surface is carbon face and the oxide is 1.4 micron on the surface, while the sidewall is only 300 nanometer, okay? So bonding is got its own intricacies, as well as the grinding and polishing is requiring an additional type of grinding tools and slurries and pads that are suitable for silicon carbide. So you go through all this hassle to process this device for what? Well, this is why we did it, which was so exciting back in 2020 when we got this result. So this is a square lamé resonator. So do you remember those distributed lamé ones? Is a bunch of these next to each other. This one is only one of those lamé modes, as you can see here. And we have phononic crystals integrated in the support structure to minimize the acoustic loss into the substrate. And what we measured was a Q of 20 million at 6 megahertz. Okay? So this is, to date, the highest acoustic Q that is measured in a MEMS resonator. And we actually expected it. We wanted to get even to higher Q factors. So this is already 5 times higher than silicon can even, in a suspended structure can get to. But it's not quite, we have another 5x to go before we are limited by the Achiezer loss of silicon carbide. Now, we were also very much interested in using silicon carbide for a gyroscope application. And this is where silicon carbide shines, which is in the 4H polytype, the hexagonal lattice will cause the split between the gyroscopic modes to be extremely small as a function of process variation, which is a huge difference compared to silicon. So not only you're going to get to higher Q, you're also going to get these two modes to be extremely close to each other as fabricated. So this is the work of Zhenming Liu, my hero PhD student who just graduated a few months ago. This is a silicon carbide disc resonator. It's a disc gyroscope, and you see the process is so well developed, you can wire bond to all of these pads. This is the SEM picture of the device, and this is how smooth the side vaults of the silicon carbide is. And the device that is about 3 millimeter in diameter shows a Q of 4.6 million in the mode match condition, and an ARW that is now about 10x better than what I showed in the silicon device earlier. Okay? Now, why is this important? Because inertial navigation is important. What is an inertial navigation system? So immediately we think about GPS, because we are so used to GPS, right? We are addicted to GPS. We can't function without GPS. Not knowing that GPS is very, very vulnerable. So God forbid if one of our enemies decide that they want to bring down all the satellites, there won't be any GPS. So DoD is very concerned about the possibility of that happening, and they are funding development of these inertial measurement units, which can actually do your navigation by measuring your motion. Okay, instead of transferring signals between ground and the satellite, you just use accelerometers and gyroscopes to measure your linear and rotational motion, and you do some processing to basically know what your position in time and space is. Okay? Now, you think about GPS being, not all the time available. It can happen also in parking lots, in canyons, bridges, tunnels. So it's not just in the doomsday scenario. In our everyday life, especially if you're thinking about drone navigation or smaller objects, you got to have a more granular, higher resolution mode of navigation that is enabled by IMUs. But more importantly, space is the final frontier, and you won't believe yourself how much funding is going into a space industry right now. There is going to be huge activities going on in the space within 100 years. So people are going to be navigating things in space, and as such, they need very small IMUs, inertial measurement units, to create these assured navigations for autonomous vehicles. And what the silicon carbide can enable is that it can outperform optical gyros that are, even today, the best known gyros that are available in the market, but they are bulky and expensive. So this ring laser gyro is what is used in most very accurate navigation. It's actually sold for about $100,000 for a pop and is still consuming 1 watt of power. And now we are on our way to actually replace that with silicon carbide devices. So silicon carbide has the ability to break into the navigation grade while silicon devices are plateauing in performance. So MEMS is going to flourish for years to come, I think not just through silicon carbide, through a variety of other materials for other type of applications. For example, aluminum nitride turns out that if you dope it with scandium, you can get to a much higher piezoelectric coefficient and much better performance compared to just pure aluminum nitride. On top of it, it becomes a ferroelectric material that you can use the ferroelectricity now to turn the resonator on and off by application of a DC voltage. So you don't need any switches to be integrated with these devices. You can just apply a DC voltage to turn them on and off. So future directions in terms of resonators is bright. And I want to show you this example from, again, another former student of mine, Ruzbeh Tabrizian, who is at the University of Florida. This was just recently, I'm sorry, this is 2024, it's not 2014. This is very recent, 2024. And what you see here is that is a silicon fin, very much like a FinFET, that is coated by piezoelectric layers deposited through an ALD process. So this is hafnia zirconia layer of piezoelectric material. It's a ferroelectric, but you can use it as a piezoelectric as well. And you can actually now use this fin, the three-dimensional fin devices as resonators for frequency filtering applications. So there will be a lot of space for material exploration, for structures, 2D versus 3D, tight coupling with CMOS in arrays. Arrays of resonators can be used for enabling still holy grail type of problems like e-nose, electronic nose. We've been working at it for a long time. We still don't have a solution. I have high hopes that gravimetric devices, when integrated with other modality of sensors, would be able to address that e-nose issues. And now looking to a space application, extreme environments. And I want to spend 5 minutes to talk about quantum atomic MEMS devices, which will enable atomic MEMS instruments. So atomic devices typically use with vapors of atoms like rubidium, okay? So a few years ago, Chandra Raman of the School of Physics and myself, we got together and we started thinking about, okay, how do we integrate atoms with silicon MEMS and use them in conjunction with those to basically get to more stable or higher performance devices, because atomic devices are known to be one of the highest performing devices that are out there. So one of the things you got to do first is to collimate the atoms. So basically you create, oops, sorry, my fingers touch this. So there's a reservoir, you basically create a vapor of rubidium, let's say, and then you have to collimate them, put them on a straight line, and then you go through these interrogation zones, sensing, detection, and cooling, excitation. So we were thinking about using wafer level processes and lithography to basically enable planar integrations of these atomic devices and systems. And by doing that, we can then further down the road integrate them with electronics and photonics to create a fully integrated system on a chip. So these silicon collimators, they're pretty neat. So we etched channels into silicon using deep RIE. We can easily control the dimensions. And then you bond another wafer on top of it to create these buried channels. And now these buried channels can be used as those collimators that I mentioned to you. So if you put a bunch of rubidium atom here and you run it through that collimator, you would see that they all get collimated. So this blue line here shows you that all the rubidium atoms are being shot from those tubes, from those channels in the straight line, which is ideal for all sorts of sensing applications. Now, one thing that is enabled because of lithography is that you can have what is known as cascaded collimators. So not just one collimator set of channels, but 3 of them in cascade, like this, L1, L2, L3, and that would create the same on-axis flux, but greatly reduce the off-axis flux. So basically, the purity of the resonances become much, much better as you cascade these collimators. It's becoming like a high-Q resonator almost. So the quality of sensing becomes a lot better in that case. And on top of that, people still are interested in further collimating and cooling the atomic beam that is coming out of these collimators. So they do that using laser beams. And for laser beams, it's very hard to actually get the laser beam to be exactly at 90-degree angle to the path of the atoms. So it is important to have these mirrors integrated with these collimators that would deflect the lights to a certain direction that is desirable, and just have it interact with the atoms and make it, cool them via that interaction. So we talked about using wet etching. We know that the KOH etch creates these 1-1-1 surfaces that you can use as a mirror. But having spent about 2 years now on that, we have learned that the KOH surfaces, even with all the efforts to make it very polished and smooth, is not good enough for creating a quality mirror that can be used in these atomic experiments. So this is one experiment that Chandra's student, Chao Li, did by just mounting a planar mirror on the edges of a 1-1-1 etched, KOH etched silicon. And what we were able to show was that by this cooling via the laser cooling, we could get this beam to be much sharper after the laser cooling, which is again the first of its type shown in this work as a fully integrated solution. Now you may say that this is not fully integrated because that KOH etched surface didn't work, and now we're working on creating planar mirrors that then can be bended down to any degree that you want, and to create these 45-degree electrodes. And this is one example of how these mirrors are going to look like. So you see how bright this is. So this is exactly similar to what a macro scale mirror quality would be for deflecting lights from one direction to the other. Just take a look at this. So this is the mirror being actuated. So at demand, you can actuate it down and it will cause the lights to be deflected. Okay, so conclusions. I think we're going to see a lot of atoms in the future being interrogated by electronics and photonics, by optical beams, and integrated with MEMS devices. So those are going to be needed for ultra-stable sensing instruments. And those ultra-stable sensing instruments can be oscillators, magnetometers, seismometers, and gyroscopes. And they're not going to all have defense applications. A lot of them will have even biomedical applications for detecting various small magnetic fields that is resulting from our brain activities, for example. There are a lot of new DARPA programs. So there is definitely programs around positioning, navigation, and timing. We talked about gyros and accelerometers. But there is a brand new DARPA MEMS program called Levitas, which is levitating and trapping of microsystems. So we want to look at how we can levitate a microsystem to get rid of some of these undesired packaging effects that would limit the stability of these instruments. So a lot left to be done. And just this one slide is a quick acknowledgement of my current and former GT colleagues. These guys, I'm happy to say that more than 50% of these guys are at the startups right now, which is great. This is what we want to see. Commercializing technologies that came out of Georgia Tech, or working with other teams to commercialize MEMS technologies. I also want to acknowledge our partners, Ramon's lab at Georgia Tech IEN, of course, for all the fabrication facilities that is available to us, as well as EVG, DISCO, SPTS, Plasmaterm, and STETX and Wolfspeed. And also support from Army Research Lab and the SEMI-PNT program. So with this, I'm going to stop and ask if you would like to ask any questions. Thank you.
Time for maybe one or two.
I took longer.
Thank you, Farrokh, for a good talk.
Hi, Eric.
Hi.
Thanks.
I guess my question is on the sensing side of things. I was just kind of curious what the mass sensitivity typically is, or maybe it's per unit area. I was just trying, it's a physical quantity when you talk about these Q factors that I can kind of get a feeling for what that means.
You're talking about the gravimetric sensors for gas sensing, or in general for?
Just, I guess in general, I mean.
Yeah. So again, you want to think about Q as a measure of force sensitivity, right? So you saw that the higher the Q, the higher this displacement as a function of a given force. So when you get to Qs that are in million or higher, you're basically getting a passive gain equal to 1 million or higher. So that's very desirable, right? Now, what are the challenges associated with this? Well, that would enable part per million to part per billion of sensitivity when it comes to biochemical sensors, right? It's not the only factor that is determining the resolution, because the narrower that line width is, the better your chances of detecting the smallest change in the frequency of the oscillator, right? So when the Q is low, there will be a sideband so that your signal will be buried in noise. So you want that higher Q to be able to detect the smallest shift in the frequency. So that's one direct way of thinking about why Q is so important for this type of application. For any other application, when it comes to, let's say, gyroscopes, you think about the Coriolis force causing coupling between the two modes. So if the Q is higher, you get that much larger amplitude for a very small force, the Coriolis force. So that's, again, why the Q is important. And, but in terms of where we are in terms of mass sensitivity, we are able to detect single molecule, but in controlled environment. So you can get to sub-attogram masses, zeptogram. So it is, so I'm just quoting you not per area, per device. These are the numbers that I've seen. So per area, it really depends on what the Q of that resonator is, because some of these smaller resonators use bending modes that are not high Q, and they may not have as high of a resolution compared to the bulk modes. So I cannot quote you a per area because it's so much dependent on the resonator design.
An attogram, just to give sort of first order, what size of resonator would that be?
It is going to be in the order of 10 micron by 10 micron, not more than 100 by 100 micron, definitely. So we can definitely envision making arrays and it still be in a millimeter size chip. Yeah, sure.
All right, I think in lieu of the time, we'll end here and thank Farrokh one more time.
Thank you so much. Appreciate it.